Alaikum wa rahmatullah. My name is Aliyu Usman, PhD student from the University of Technology Petronas. I'm here to present my paper titled Engineering Properties of Irradiated Waste Polyethylene Terephthalate Modified Asphaltic Concrete Mixtures using the Modified Dry Process. The background of the paper is polyethylene terephthalate, which is a thermoplastic polymer of the polyester family. It's a non-biodegradable type of polymer which can remain in the earth for years or decades without decomposition. So there is urgent need for the reuse of this waste as alternative material in asphalt concrete materials as aggregate. And there are so many motives behind the use of waste materials in highway industries, one of which is to use this waste material to replace natural resources which are sourced from non-renewable sources. Also, gamma irradiation on polymers. It has been proved that when polymers are exposed to gamma radiation, there is two effects that normally occurs to the polymer, which are transition and cross-linking. So when polymer is irradiated, the degree of transition increases, and then which makes the plastic to become stiffer, tougher, and harder. The background continues as there are a contribution of waste material used in environment to the environment and economy, one of which is to diminish the abuse of natural resources, and it contributes to saving energy and money. The problem statement of my paper is as follows. Waste disposal crisis due to the nature of polyethylene terephthalate. We have when PET is used, only small amount of this PET is used, and there are some logical inconsistencies reported on the mechanical properties of the modified asphalt mixtures incorporating this waste plastic. So also Malaysia is among the top countries that have the highest number of mismanaged plastic globally. So there is urgent need to required to initiate an effective or systematic solution for managing waste plastic. Objective of the paper is as follows: to investigate effect of irradiation on waste plastic as partial aggregate replacement on dense graded asphalt mixtures on the density, void, and moisture parameters, and to determine the optimum content of this plastic that will result in enhanced engineering properties. The methodology is as follows, as you can see based on the slide. We have materials, gamma irradiation, optimum binder content optimization, density, void, and moisture parameters evaluation. In this paper, the optimum binder content for the control is used for the preparation of modified asphalt concrete mixtures. The methodology continues as when first is to acquire the material, then test on the materials to ascertain its stability for use as pavement materials. Then we have the determination of optimum bitumen content, which, as mentioned earlier, that the bitumen content of the control will be used for the modified mixtures. Then we have two types of modified mixtures, which is one containing regular PET and the other one containing irradiated waste polyethylene terephthalate. After which the volumetric properties and moisture parameters test will be conducted, and then comparison of these volumetric properties of three mixtures, that's the control, regular waste PET modified mixture, and irradiated waste PET modified mixtures, will be carried out, and then based on the comparison, conclusion we made. This figure, result and discussion, is showing the plots for the optimal asphalt content evaluation. As you can see, plot A to D is showing how bitumen content affect the bulk density, air void, stability, flow, and the BFA. These 5 plots were used to obtain the optimal asphalt content. First at maximum density, at 4% air void, at maximum stability, at 3 mm flow, and then at 75% BFA. All these were selected based on JKR standard specification for roads. So also after exposing this PET to gamma irradiation, there is need to check the effect of irradiation on the properties of this PET. So FTIR and TGA were carried out to ascertain the effect of this irradiation on the PET. On the FTIR, there is no any effect of gamma irradiation on the functional group of the PET before and after irradiation. As you can observe from the plot, we have the same wave band for both regular and irradiated PET, but on the thermal analysis using the TGA, we observe some differences. There is increase in the degree of decomposition, initiation decomposition temperature of the PET after irradiation, which validate the effect of cross-linking after exposure of gamma irradiation, and which makes this plastic to be more stable thermally when irradiated. The discussion continues with the density, the effect of this PET on the density, as expected, definitely, because the unit weight of this aggregate is less compared to that of the conventional mineral aggregate. Therefore, there is decrease in density as the waste PET content increase in the mixture. So also looking at the waste PET modified mixture and the irradiated waste PET modified mixture, as you can see, the irradiated waste PET is having higher density compared to regular waste PET. This as a result of molecular weight decrease as a result of transition that occurs during irradiation. So also the air void increases with increase in the content of this PET. This can be attributed to the elastic deformation of the plastic when used to replace conventional aggregate, which elastic deformation under compaction effort. The next figure is the effect of this PET on the BMA and BFB, which are part of the void analysis. As you can see, BMA is increased with reduces at lower content of this. It increases and then reduces and then later increases. This can be attributed to the behavior of the density and air void content as described earlier, as the BMA is directly proportional to the air void. So as the air void increases, definitely the BMA will be increases. And so also the density affects the BMA. As the density is higher, then definitely the BMA is going to be lower. Then the BFB shows that the regular PET, the waste modified mixtures, both regular and irradiated, are having higher BMA at 1 and 3%. Then at higher content of the PET, the BMA is lower than that of the control. But notwithstanding, both the regular PET modified and irradiated PET mixtures have BFB within the code specification. This is showing the mass stability and flow. As you can see, the stability increases in the PET content for both mixtures, but the irradiated PET is having higher mass stability compared to the non-irradiated PET mixtures. This is as a result of the gamma irradiation effect, which makes the PET to be constantly to increases, and then it covers the void between aggregate and makes the mixture stiffer. Then the flow increase with increase in the PET content, but the flow values are within the core specification of the JK specification. This showing the next figure is showing the Marshall quotient. The stiffness of the mixture is less than that of the control, but is higher for PET content containing for irradiated PET mixture containing 5% irradiated PET content. Based on the analysis carried out, the conclusions are as follows. As you can see, the stability increases, and then due to the lack of time, I can stop here. Thank you for listening.